Can you see my screen?
Yes.
This we have discussed the mechanism for primary halogenoalkanes in the last class. Okay, so I told you this, that here a nucleophile comes, it attacks to the carbon which is bearing the leaving group, and the leaving group leaves in the one step. This is the one-step reaction. So this is the explanation of this. So have you noted it down in your notebook?
I think I've already noted this.
Yes, so this is done. Yes, so this mechanism which we have discussed here in the yesterday's class, which is called an SN2 mechanism. S means your substitution, N means nucleophilic, and 2 means that the rate of reaction which is determined by the slow step in the mechanism, it involves two reacting species. Okay, it involves two reacting species. What are the two species? One species is this. One species is this, and the one species is this. So these are the two species which are involved in the reaction here. Okay, experiments show us that the rate depends on both the concentration of the halogenoalkane, that is ethyl bromide which we have taken, and the concentration of the hydroxide ions present. So you should know that the rate, it depends on the concentration of halogenoalkane and concentration of hydroxide ions. So that's why it is a second order reaction. So this 2 means that it is a second order reaction. Write it down. Now, next is your mechanism for the tertiary halogenoalkanes, which is also known as your SN1 reaction. So, in the SN2 reaction, we have discussed the order of rate. In SN2, you have 1 degree, then 2 degree, then 3 degree. This is the order of rate. But in SN1, it is specifically for 3 degree, then 2 degree, then 1 degree. Halogenoalkane. In a tertiary halogenoalkane, carbon atom bonded to the halogen atom is bonded to 3 other carbon atoms, that is your alkyl group. For example, 2-bromo, 2-methylpropane. 2-bromo, 2-methylpropane, how to make? This is propane, this is 2-bromo, and this is 2-methylpropane. Okay, so this is a 3 degree halogenoalkane because this carbon atom, it is connected to 3 other carbon atoms. Okay, so this is a 3 degree halogenoalkane. Now the carbon atom bonded to the bromine atom is attached to 3 alkyl groups, that is your methyl groups. So the structure of this tertiary halogenoalkane is something like this. Okay, then how nucleophile approaches in this case, we'll see. First of all, write this down. Here also the same thing happens. The nucleophile will come and your leaving group will leave.
Done.
Okay. So this is the tertiary halogenoalkane, 2-bromo, 2-methylpropane. So this reaction is your two-step mechanism. SN1 is a two-step mechanism, while SN1 is a two-step reaction, while SN2, so this is the difference. It is a one-step reaction. In one step, your nucleophile is coming, and in that step only your leaving group is leaving. But SN1 is a two-step reaction. How two-step? Let us see. First step in the mechanism is the breaking of the carbon halogen bond. So first of all, your carbon halogen bond will break like this. Carbon halogen bond will break, and if this bond will break, you know that it is partial negative, this is partial positive. So this carbon get positive charge. This bond have 2 electrons. So bromine takes both the electrons and leaves. So this carbon have positive charge. So first step is the formation of carbocation. First step in SN1 reaction is the formation of the carbocation. Okay, this is a 3 degree carbocation, and we know that 3 degree carbocation is stable. Why 3 degree carbocation is stable? Suppose we have a carbocation like this. It is stable because carbocation means it is electron deficient. Okay, and these CH3 groups, they exert plus I effect. They are donating the electrons. This is also donating electrons. This is also donating electrons, and this is also donating its electrons. That means they are neutralizing this positive charge. Okay, they are making this positive charge less intense. Then the tertiary carbocation is attacked immediately by the hydroxide ion. Then what happens? Your nucleophile is hydroxide. So this negative charge attacks here, and we have this kind of product. So this is the mechanism of nucleophilic substitution reaction in a 3 degree halogenoalkane. So if any step is not clear, so please let me know that this is partial negative, this is partial positive because CBr bond is polarized. So bromine takes both the electrons, okay, towards itself. Formation of carbocation will happen in the second step. Then the nucleophile will come. Nucleophile will come and it will attack this positive sign, positive carbocation, and we have this as a product. You have to remember that this is a slow step, which is your rate determining step of the reaction, and this is your fast step. Okay, so why this is fast step? Because it is unstable. This molecule is unstable because this is intermediate, right? Carbon have only 3 valencies, so it is unstable. So it wants to complete its 4 valencies. That's why this reaction is a fast reaction. And why this step is a slow reaction? Because here carbon is having 4 bonds, it is stable, but here carbon is having only 3 bonds, it is unstable. So that's why this reaction is slow, which is the rate determining step of this reaction. Clear? So write it down.
Yes, done.
Okay, so this mechanism is known as SN1 mechanism. You know the meaning of all these 3 terms. S means substitution, nucleophilic, and 1 means unimolecular. Unimolecular. Unimolecular means that the order of reaction is 1 here. Order of reaction is 1. So this one tells that the rate of reaction only depends on one reagent, in this case the concentration of halogenoalkane. So rate only depends on the concentration of halogenoalkane. Here the rate is not depending on the nucleophile. Okay, that's why it is only first order reaction. As shown, why it is so? Because rate is determined by the slow step of the reaction, and in the slow step only your involvement of this halogenoalkane is there. Okay, because in the fast step nucleophile is coming. So that's why the rate is dependent on the concentration of halogenoalkane only. Once again, this breaking of the CBr bond is an example of your heterolytic fission. Write it down.
I'm done.
So the theoretical part is written here. I hope the mechanism is clear. That bromide ion forms again as in the SN2 mechanism. But in this mechanism, a carbocation ion forms. Carbocation forms only in the SN1 mechanism, not in the SN2 mechanism, remember. This does not happen with primary halogenoalkanes. Okay, this is because, why it doesn't happen in primary halogenoalkanes? Because primary halogenoalkanes, they are not as stable as tertiary carbocations. As you know, carbocations, the stability order of carbocations is 3 degrees most stable, then 2 degree carbocation, then 1 degree. Why it is so? Because the CH3 groups, they are donating electrons to this carbocation. Okay, carbocation is electron deficient, and the CH3 groups, they are donating electrons to this carbocation. So they are making the carbocation less intense.
Hey students! Interested in boosting your studies? Enroll now at Keddy Edtech. We offer online tuition for the Cambridge curriculum, grades 6 to IGCSE, AS, and A-level. Start learning with us today.
Less intensified. So this is because tertiary carbocations are more stable than primary carbocations due to the positive inductive effect of the alkyl. Inductive effect means donation of electrons to the carbocation. So attached to the carbon atom bonded to the halogen. Alkyl groups tends to release electrons to atoms attached to them. So a tertiary carbocation has 3 alkyl groups donating electron towards the positively charged carbon atom. So the same thing is there, which I already explained, that this is your tertiary carbocation. It has 3 alkyl groups. They are donating electrons to this carbocation, right? They are donating the electrons to this carbocation, reducing its charge density. This makes it more stable than a primary carbocation, which just has 1 alkyl group releasing electron. If it is a carbocation, it has only 1 CH3 group, all other are H groups. Then electrons are coming from only 1 CH3 group. So that's why it is not as stable as 3 degree carbocation. Okay, write it down.
Yes.
So I hope now you can differentiate between SN1 reactions and SN2 reactions. We discussed both the reactions SN1 and SN2. Okay, it is substitution nucleophilic unimolecular, and it is substitution nucleophilic bimolecular. So in this reaction, SN1 reaction, as you know that tertiary carbocation is more stable. So 3 degree, 2 degree, 1 degree in SN1. But in SN2, it is 1 degree, then 2 degree, then 3 degree. Why? Because no carbocation formation is occurring here. Second thing is that in SN1 reactions, if we talk about steps, then there are two steps in the reaction. First step is carbocation formation, and the second step is where nucleophile is attacking. But in SN2 reaction, step is only one. As the nucleophile is approaching, at the similar time, your leaving group is leaving. So step is one. If we talk about order, then you know that it is a first order reaction whose rate only depends on the concentration of the halogenoalkane. But in SN2 reaction, its order is 2. Why? Because here rate it depends on the concentration of the halogenoalkane as well as the concentration of the nucleophile approaching. Okay. So here it is a primary carbocation 1 degree, it is a secondary carbocation, it is a tertiary carbocation. You know which is more stable? 3 degree is more stable, then 2 degree, then 1 degree. These arrows are showing the displacement of the sigma electrons to this positive charge. Positive charge means itself it is electron deficient. So you are making it less deficient by donating electrons to it. Okay, so this is the trend in the stability of primary, secondary and tertiary carbon. There is one more difference we will study, that in SN1 it is favored by polar protic solvents which can donate your H plus easily. But in SN2 reactions it is favored by polar aprotic solvents which do not release their protons. So if any question you see polar protic solvent, so it is SN1. If any question you see it is polar aprotic solvent, so it is SN2. So the work is same, that nucleophile is coming and the leaving group is leaving, but the mechanisms are different. Write it down.
I'm done.
I'm done.
Okay, so this is these two questions are your homework. That draw the structure, discrete formula of 2-chloro-2-methylbutane and show the mechanism for the hydrolysis of 2-chloro-2-methylbutane by an alkyl. Okay, so write it down. Two chloro 2-methylbutane is primary, secondary or tertiary? Halogenoalkane. Which halogenoalkane is it? Draw the structure and tell me. Is it tertiary, primary or secondary halogenoalkane? Is it so hard?
I think it's tertiary.
Yes, it is tertiary halogenoalkane because this halogen atom which is attached to this carbon, it is connected to 1, 2 and 3 carbon atoms. So it is a tertiary halogenoalkane. So you have to show the mechanism by an alkyl. Okay, so it is, I think you know it is SN1 reaction now because tertiary carbocations are more stable. Done writing your homework questions?
Yes.
Yes.
Next reaction is your elimination reaction. So we have discussed substitution reactions SN1 and SN2. Elimination reactions in which a small molecule eliminates like water. Okay, so in halogenoalkanes, the major reaction is elimination reaction also. Elimination, as the name suggests, loss of a small molecule from the original organic molecule. So small molecule may be HCl, it may be HBr. Okay, so depending on the reagent used, the small molecule is eliminated. It is very easy. The agent which is used in this elimination reaction is ethanolic sodium hydroxide. Sodium hydroxide, NaOH, taken in ethanol. It is known as ethanolic sodium hydroxide. You heat it, heating is necessary. In elimination reaction, heating is very necessary. So you heat the halogenoalkane. Now what happens if we draw the discrete formula? So it is CH3CH2Br. When you heat it with ethanolic solution of sodium hydroxide, then what happens? This is my alpha carbon, this one which I have highlighted, this is my alpha carbon and this is my beta carbon, which is next carbon is beta, this is alpha. So from alpha you have to remove halogen, from beta you have to remove hydrogen and you have to put a double bond between alpha and beta. So it becomes CH2 double bond CH2. So it is your one and only ethene, okay? So which molecule is eliminated from here? HBr. HBr is eliminated. H from beta and bromine from alpha. If it is NaOH used, then it is NaBr which is eliminated. Okay. So original bromoethane molecule, it has lost two atoms, hydrogen atom and bromine atom. We can think of it as HBr being eliminated from the halogenalkane, but the ethanolic OH minus ion act as a base, and the work of base is what? The work of base is just to accept the acidic hydrogen. So it accepts an H plus ion from the halogenalkane to form water. Okay, so that's why this water is forming. The Cr bond breaks heterolytically. So this step is same as SN1 and SN2 because this bond is polar, where carbon is having partial positive charge and bromine is having partial negative charge. So it will break heterolytically. Both the electrons are taken up by bromine. So it forms a bromide ion and leaving an alkene as the organic product. So basically major product is important, and this reaction is also known as dehydrohalogenation. D means removal, hydro means removal of a H, halogen means your chlorine, bromine and iodine. So both atoms are removing, that's why it is known as dehydrohalogenation reaction. Is it clear?
Yes.
Yes.
Write it down. Here also we will study two reactions, E1 and E2.